The better our model of matter, the more we can understand about matter itself, and the more uses we can make of that understanding. Models of matter help us understand the chemical process that affect every aspect of modern life, from nourishing our bodies to fueling space shuttles. You are already familiar with one model, the particle theory, which states that all matter is made of tiny particles. Like all models, this model is a mental picture, a diagram, or a three-dimensional means of representing something. For instance, the particle theory can be used to help understand physical behavior of substances such as changes of state. It can also be applied to explain the formation of various models from different combinations of atoms, but what makes atoms different from each other? Look at the illustrated model. What is inside the particle we call an atom? Over time, it becomes more and more clear to scientists that the particle theory could not explain all observable behaviors of matter. New evidence required that new models be created. For instance, the particle theory is not useful for understanding static electricity. Why do we sometimes get electric shocks when we touch a metal doorknob? Why is dust more attracted to your television screen than to your television cabinet? How can a different model of matter be used to answer these questions? How do fireworks produce dazzling displays of light, color, and sound? The answer lies in the nuclear model of the atom. What are some other practical applications of this model? Imagine that you are standing in front of a pop vending machine, figure 1. You put in a coin, press a button, and a can falls down into the tray at the bottom. How does the machine work? You can't see inside it, so you have to create a model that could explain the workings of the machine. One possibility is that there is a very small person working inside. When the coin appears, the person checks to see which button was pushed, searches for the right can, and puts it in the tray. A second possibility might involve a mechanical system with various electronic sensors, levers, motors, and slots that operate when the coin is inserted to release the can. How could you test these hypotheses? You could pull out the electric plug in the back. If no can appears when the power is off, perhaps the second hypothesis is correct. Or maybe the person inside refuses to work in the dark. The first hypothesis is still a possibility. The best model you can create is the one that allows you to predict how the vending machine will behave in as many situations as you can imagine. You may come up with a model that works perfectly for all the evidence that you have, but someone else might try using the vending machine in a completely new situation. If the can doesn't fall and the model can't explain it, then the model needs to be adjusted. Like a scientist exploring models of matter, all of your testing, thinking, and experimenting is based on the fact that you can't see what's going on inside the vending machine. Atoms can't be seen. We can only see how matter behaves in certain circumstances. The model of matter changes when the model is tested in new circumstances that produce new and unpredictable results. In this investigation, you will follow a similar process by trying to guess what is inside a sealed box. You will use some basic scientific skills, gathering and organizing observations, inventing a model to explain these observations, and communicating your findings to others. Making connections. 1. Think about the original example of the vending machine. A. What experiments could you do to find out how the vending machine operates? B. Draw a model of how you think the machine operates. 2. Choose an everyday appliance. Draw and label a model to explain how it works. Suggest ways that your model could be tested. Exploring. 3. Obtain a polystyrene sphere in which your teacher has embedded an object. Take a thin metal probe or knitting needle and carefully insert it into the sphere. Make a systematic series of probings, record your observations, and make a model drawing to describe what is inside the polystyrene atom. Reflecting. Think about your group's success with determining the identity of the object in the box. Is there any reason why you successfully determine some characteristics but not others? Developing models of matter. Have you ever taken something apart to figure out how it works? Have you ever watched the sand wash away from around your feet as you stand at the edge of the ocean? Like scientists and philosophers through the ages, you are curious about the world around you. You want to know how things will behave in certain circumstances. Perhaps you will develop an idea about something and test it. In just the same way, scientists have observed, questioned, and theorized for centuries about the stuff that makes up the world, matter. They looked at the evidence around them and, in an attempt to explain it, developed many models of matter. These have been modified, combined, or rejected as new evidence was discovered. Figure 1. According to the four-element model, each element is a mixture of two properties. For example, fire is a mixture of hotness and dryness. About 450 BC, a Greek scholar named Empedocles proposed that matter was composed of four elements: earth, air, fire, and water, in Figure 1. These elements mix together in different proportions to yield different substances. Rust might be 1 part fire and 2 parts earth. Volcanic rock might be 2 parts fire and 1 part air. Unlike most philosophers of his time, Empedocles checked some of his theories experimentally. He demonstrated that even though air is invisible, it is not just nothing. Because it takes up space, it must be a form of matter. About 400 BC, another Greek, Democritus, suggested that matter was made of tiny particles that could not be broken down further, Figure 2. Figure 2, in the atomic model, atoms were conceived to be of different sizes, to have regular geometric shapes, and to be in constant motion. He called the particles atoms after the Greek word atomos, which means indivisible. Thus, different elements were composed of different kinds of atoms, a revolutionary concept at the time. However, Democritus's ideas were never widely accepted because Socrates, a very influential figure at the time, did not accept them. Figure 3. The Greek philosopher Aristotle also believed that matter was made of four elements: earth, air, fire, and water. About 350 BC, philosopher Aristotle believed in Empedocles' four-element model despite the more recent atomic model in Figure 3. Aristotle's influence was so great and his writings read by so many people that the four-element model was accepted for almost 2,000 years. AD 500 to 1600. Do metals grow like plants, ripening into gold? Many alchemists, combination of philosopher, mystic, magician, and chemist, believed that they did. For centuries, they performed numerous experiments attempting to make gold from cheap metal, such as iron and lead. They devised chemical symbols for substances that we now recognize as elements and compounds. They also invented many laboratory tools that we still use today: beakers, filters, stirring rods, and distillation apparatus. However, despite finding many new substances, they still accepted the four-element model, and no one ever turned lead into gold. 1650. An English scientist, Robert Boyle, did not believe in the four-element model. He devised a new definition for the word element. I mean by element simple, unmitigated bodies. This became the modern definition of an element, a pure substance that cannot be chemically broken down into simpler substances. Boyle also believed that air was not an element, but rather a mixture. Late 1700s. Joseph Priestley was the first person to isolate oxygen scientifically, but he did not know that oxygen is an element. This fact was soon recognized by Antoine Lavoisier. Figure 4. Antoine Lavoisier is often considered the father of modern chemistry. His involvement in a state organization that collected taxes led to his execution by guillotine in 1791 during the French Revolution. Experimenting with Priestley's oxygen, Lavoisier concluded that air must be a mixture of at least two gases, one of which was oxygen. Meanwhile, Henry Cavendish experimented by mixing a metal with acid, which resulted in an inflammable gas that was lighter than air. He did not know that the gas he had prepared was hydrogen, but discovered that his gas would burn in some of Priestley's oxygen, producing water. Figure 5. When Cavendish burned hydrogen in oxygen, he produced water. So there's a jar, there's a source of hydrogen, at the bottom is pure oxygen gas, there's a flame, and the water droplets is the evidence that water is being produced. Until that time, scholars had believed that water was an element. By this time, it was generally accepted that matter was made of elements. The two models had come together. English chemist John Dalton published a theory of why elements differ from each other and from non-elements. Figure 6. Figure 6. In Dalton's atomic model, an atom is a solid sphere. This model is still useful for explaining chemical charges. Atoms combine and molecules come apart as chemical reactions occur. Dalton's atomic model for matter stated that all matter is made of atoms, which are particles too small to see. Each element has its own kind of atom with its particular mass. Compounds are created when atoms of different elements link to form molecules. Atoms cannot be created, destroyed, or subdivided in chemical changes. 1800s. However, Dalton's atomic model cannot explain why, on a dry winter day, you get a spark when you touch a metal doorknob. Obviously, matter is able to develop positive and negative charges, quantities of electricity that may build up on an object. A new model was developed introducing tiny negatively charged particles that could be separated from their atoms and moved to other atoms. In 1831, Michael Faraday found that electric current could cause chemical changes in some compounds in solution. The atoms could gain electric charges and form charged atoms called ions. In this modified version of Dalton's model, matter must contain positive and negative charges, opposite charges attract, and like charges repel. Atoms combine to form molecules because of electrical attractions between atoms. 1904. J.J. Thomson revised the atomic model further to explain his discovery of very light negative particle called electrons. He also did experiments with beams of much heavier positive particles, later identified as protons. The new model became known as the raisin bun model, or the plum pudding model in other books. Figure 7a. In Thomson's model, the atom is a positive sphere with embedded electrons. Atoms contain particles called electrons. Electrons have a small mass and a negative charge. The rest of the atom is a sphere of positive charges. The electrons are embedded in the sphere so that the resulting atoms are neutral or uncharged. The Japanese scientist H. Nagaoka, working at about the same time, modeled the atom as a large positive sphere surrounded by a ring of negative electrons. That's figure 7b. In Nagaoka's model, the atom is compared with the planet Saturn, where the planet represents the positively charged part of the atom and the rings represent the negatively charged electrons. 1911. Ernest Rutherford, working at McGill University in Montreal, designed an experiment to test Thomson's and Nagaoka's model. He aimed a type of radiation called alpha particles, positively charged particles smaller than most atoms, at a thin sheet of gold foil. He predicted, based on Thomson's raisin bun model, that the particles would pass straight through the gold foil, as indeed most of them did. However, a very small number of the alpha particles bounced almost straight back from the gold foil. Figure 8. Figure 8 is a representation of Rutherford's experiment. Rutherford was amazed and described the result as being similar to firing bullets at a piece of tissue paper and having one of them bounce back. To explain how the positive alpha particles had been repelled, Rutherford had to come up with another new model, the nuclear model. An atom has a tiny, dense, positive core called the nucleus, which deflected the alpha particles and contains protons. The nucleus is surrounded mostly by empty space, containing rapidly moving negative electrons through which the alpha particles passed unhindered. Understanding concepts. 1. How were alchemists similar to and different from modern scientists? 2. Describe the changing definitions of an element. 3. Describe the changing definitions of an atom. 4. What were the 4 main points in Dalton's theory? 5. Whose work led to a model that suggested that A. The atom contains a dense positive core. B. Atoms can form charged particles called ions. C. Atoms contain electrons and protons. D. Atoms cannot be divided further. E. Electrons surround a central positive core. 6. In Rutherford's gold foil experiment, what kind of electrical charge do the alpha particles have? B. What might Rutherford have expected to observe based on Thomson's model? C. What is the relative size of the heaviest part of the atom compared with the whole atom? Exploring. Number 7. Design an experiment to demonstrate that fire and earth are not elements. 8. Design and build a model to represent one of the early models of the atom. Reflecting. Number 9. Why do scientists continue to make models of matter if the models keep changing? Write a few sentences to suggest why models might be useful. Inside the atom. What does splitting the atom mean? And if the atom is split, what do the pieces look like? Rutherford's experiment was a breakthrough in how people thought about matter. As you have learned in the nuclear model, most of the atom is empty space, filled with quickly moving electrons. The positive nucleus is so small that it takes up only a tiny fraction of the size of the atom. Yet, almost all of the atom's mass is concentrated in this nucleus, which contains protons. Types of subatomic particles. The pieces of an atom, the particles of which an atom is composed, are called subatomic particles. Electrons and protons are subatomic particles. Experiments conducted by the English scientist James Chadwick in 1932 led to the discovery of a third subatomic particle with no charge, the neutron. These subatomic particles are described in terms of their mass relative to each other, their electrical charge, and their location. Protons are positively charged particles with a relative mass of 1 located in the nucleus. Neutrons are neutral particles with a relative mass of 1, also located in the nucleus. Electrons are negatively charged particles with a relative mass of approximately 1/2000th of the mass of a proton or neutron, traveling in regions of space around the nucleus. Protons are especially significant because the number of protons in an atom determines what the atom is. For example, any atom with 1 proton is a hydrogen atom, H, and any atom whose nucleus contains 12 protons is magnesium, Mg. Counting subatomic particles. How many electrons, protons, and neutrons are there in an atom? An atom itself has no electrical charge, and the negative charge of 1 electron is as strong as the positive charge of 1 proton. The number of protons and electrons in an atom is the same. So the charges cancel each other out. Some examples are given in Table 1. When the number of protons equal the number of electrons, that's called the ground state of the atom. Table 1 lists hydrogen, oxygen, magnesium, copper, and uranium. They list the number of protons, the total positive charge, the number of electrons, the total negative charge, and the net charge of an atom in the ground state. The number of protons in an atom is called the atomic number. If you know the atomic number of an atom, you know how many protons and how many electrons that atom contains. Another significant number is the mass number. The mass number represents the sum of protons and neutrons in an atom. The mass of the electrons relative to the mass of the protons and neutrons is insignificant. Therefore, if you know the atomic number, the number of protons, and the mass number, the sum of the protons and the neutrons, you can easily calculate the number of neutrons. Number of neutrons equals mass number minus atomic number. We can represent the numbers of subatomic particles by using standard atomic notation, an internationally recognized system that allows anyone to communicate information about any atom. In this notation, we write the chemical symbol of the atom and place the atomic number to the lower left and the mass number to the upper left. For example, the atomic notation of chlorine is 35/17 next to the symbol capital C small l. Similarly, the atomic notation for an atom of sodium is 23/11 capital N small a. This notation tells us that sodium has 11 protons and 23 minus 11 neutrons, 12 neutrons. Since the atom is neutral, it also tells us that the number of electrons is 11. This sodium atom could also be represented as sodium 23. Charged atoms. Why is it dangerous to work with electrical appliances around water? Tap water and rainwater can conduct electricity because they are not pure water. They contain charged atoms that can move in the solution and carry electric current. Pure water does not conduct electricity. These charged atoms are called ions. They have a charge because the number of electrons is not equal to the number of protons. For example, salt water contains sodium ions, which have 11 protons and 10 electrons. The sodium ions have a charge of +1. Salt water also contains chloride ions, which have 17 protons and 18 electrons. The chloride ions have a charge of -1. Ions are formed when negatively charged electrons move from one atom to another. If an atom loses an electron, there are more protons in the nucleus than electrons in the space around it. Atoms such as sodium and calcium lose electrons to form such ions with net positive charges. Figure 1a. That's going back to figure 1, which is a nice illustration. It says atoms can gain or lose electrons to form charged atoms or ions. The elements are still the same because the number of protons has not changed. Continuing. If atoms gain electrons, there are more electrons than protons. Atoms such as chlorine and oxygen gain electrons to form ions with net negative charges, figure 1b. These charged particles, now described as ions rather than atoms, can move in solutions and conduct electricity. Understanding concepts. Draw and complete a table with 3 rows and 4 columns to summarize what you know about the nuclear model of the atom. The column headings should be particle, proton, neutron, electron. The row headings should be mass, charge, location in atom. Write standard atomic notation for the following: an atom of nitrogen with 7 protons and 8 neutrons. An atom of bromine with 35 protons and 36 neutrons. C, an atom of sulfur with 16 protons and 16 neutrons. You may want to look at a table of chemical symbols on page 58. Number 3, assuming that each atom is neutral or in the ground state, copy and complete table 2 by filling in the blanks. An ion is an atom that has gained an electrical charge. A. A magnesium atom has 12 protons. How many electrons does the magnesium ion have with a charge of +2? B. A fluorine atom has an atomic number of 9. How many electrons does a fluorine ion with a charge of -1 have, reflecting? If the atom is almost entirely empty space, why do atoms not just collapse into each other and into a much smaller volume? Hint, think about what you know about attraction and repulsion of charges.